All right, notes part 3. Here we go with some homework help. So, some of the questions you will be answering say something like this. Express the repeating decimal as a fraction. So we know the little bar means this is 0.25353535353. There's a cool trick that involves this where we can basically turn this into a fraction. So, here's the bottom line. If we have one repeating decimal, we're going to multiply by 10, two repeating decimals multiply by 100, three repeating decimals multiply by 1,000, etc. So that's your trick. Right here we have two repeating decimals, so we're going to multiply this number by 100 and watch what happens. We're going to say, you can choose x or n or whatever. So x equals our number, okay, that we're trying to turn into a fraction. And if we multiply that by 100, 100x, so we move the decimal 1, 2 spaces to the right. So this is x, and I 5, 3, 5, 3, 5, 3, 5, 3, etc. After moving 2 spaces to the right, 100x will be 25.35353, etc. And so this continues as 5353, and this continues as 5353, etc. If we subtract them, watch what happens. Cancel, 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 cancel. Aha. So basically, we set this up because it's a repeating decimal. All of that, when subtracted, becomes 0. So subtracting this number from this number, we're going to end up with 25.1, okay? And subtracting x from 100x gives us 99x. So all of a sudden, we have this simple algebraic equation with a number and a number, and x is our repeating decimal that we're trying to turn into a fraction, so we can divide both sides by 99, and we end up with 25.1 over 99, which it's a little neater if we actually multiply by 10 and multiply by 10 to give us 251 over 990. So this is the same thing as what was our original 0.253 repeating. Cool, huh? So that will always work. Just know how to multiply it by 10 or 100 or 1,000 or 10,000, and then you're going to end up subtracting. You're going to end up subtracting, and things will cancel, and then you can divide. And you're usually dividing by 9 or 99 or 999 in that last step. Okay. Next up, this question says, so we're sort of applying our concepts. The 10th term of an arithmetic sequence is 55 over 2, and the second term is 7 over 2. Find the first term. So, I always recommend kind of writing this out. I'm a very visual person, so I just make a little dash for each term. And I know that the second term is 7 halves, and the 10th term is 55 halves. And because it's arithmetic, I know we're adding D and D, 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 D each time. So if we count up how many D's we have added, there are 8 of them in going from 7 halves to 55 halves. So we can say in algebra, 7 halves plus 8D equals 55 halves. And from this we can solve to end up with the common difference of 3. So if the common difference is 3, we know in going from here to here, this would be 7 halves plus 3, this would be that number plus 3, this would be that number plus 3, etc. Our first term, which is what we're actually looking for, this plus 3 is 7 halves, so we can take away 3 from 7 halves to get our first term. So this is what I have here. 7 halves minus 3 is 1 half, and that would be a sub 1, meaning the value of our first term. 1 half. Okay. Is there another way? Well, probably. If that doesn't help, well, yeah, let's just leave it at that. If that's not helping you, ask in class, and you can basically plug into the explicit formula, and you're gonna have 2 formulas or 2 equations, 2 variables, I think. So we could try that. I think it'll be more difficult. Next example. the first term of a geometric sequence is 3, and the third term is 4/3. So again, I wrote out these little dashes. Here's the first term, here's the second term, third term, fourth term, fifth term is what we're looking for. So we could have a little 5 right there. Okay. So, because it's geometric, we know we multiply by r, and we multiply by r, meaning 3 times r is 4/3. This is what I wrote out right here. This whole taking a situation and describing it mathematically. Cool. 3 times r is 4/3. In other words, 3r squared is 4/3. Divide both sides by 3. Take the square root. And we get 2/3 as our common difference. And technically, negative 2/3 would also be an answer here. We end up ending up with the same value for the fifth term. So, what do we have? Third term times r. So third term times r is a sub 5, the value of the fifth term. And when we multiply, I think we get 16/27. Cool. We could also, so at this point, once you know r, and once we know this, a sub 1, we could have just substituted into our formula for the explicit formula of a geometric sequence, and this would have given us the same thing, 16/27. Alright, next page. Oh yeah, so there's some cool word problems at the end of the second section. Here's an example of one of them. It says a ball is dropped from a height of 80 feet. The elasticity, meaning the bounce, of the ball is such that it rebounds to 3/4 the height from which it fell, so 75%. So if there's 80 feet, it would bounce to 75% of that, and then 75% of that, and then 75% of that, 75% of that. It's a pretty bouncy ball. How high does the ball bounce on its fifth bounce? So we got 1, 2, 3, 4, 5. Okay, so this sounds wrong. The first bounce, alright, well, whatever, we'll get to that. How high does the ball bounce on the fifth bounce? Find a formula for how high it bounces on the nth bounce. So it looks like this. The initial height is 80, and then it's going to bounce to a height of 80 times 3/4. So where's my marker? And let's zoom in a little bit. So this is the start, and this is the first bounce, and the second bounce, third bounce, fourth bounce. So that's not the actual height. The fifth bounce would be 80 times this 3/4 to the fifth. So for the first bounce, we have 3/4 to the first, second bounce 3/4 to the second, third bounce 3/4 to the third, etc. And this number is an 18.98. And what are we talking about? Feet? Okay. So that's what we'd get for the height of the fifth bounce. The formula for, so this, don't write this. I was thinking, when I wrote this out, I was thinking this is the first bounce, but it hadn't actually bounced by that point. This is the first bounce, so I was off by 1. A general formula, you see how for the fifth bounce we have 80 times 3/4 to the fifth, and for the fourth bounce 80 times 3/4 to the fourth, etc. So this is good, except that because that 80 is not actually the first bounce. If we were to cross this out, that would be a formula for the height of the nth bounce. So each of these word problems, kind of like the problem of the week that we have been doing, is related to sequences and series. Okay, next up we have this situation. So there's a square 1 by 1, and then midpoint, right? There's another square drawn, and then midpoint, another square drawn, midpoint, another square drawn, etc., etc., etc. So what we're trying to do is figure out if we were to add up the area of this plus 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 the area of this, and keep going forever, what would we actually get? And because the squares get smaller and smaller and smaller, we say this is a converging series, and we'll actually find some value. And we're going to do the same for the perimeters of all of the squares inward to infinity. Whoa, yeah, cool. So, smaller and smaller squares are drawn inside forever. Find the area of all the squares, or sum of area of all the squares. So what I've done is I've just taken this section, and we know that because this is 1, we know each of these will be 1/2. And using our SOHCAHTOA skills, or our special right triangle skills, we know that this would be root 2 over 2. So when we go to find the area of the second square, let's see, this is the area of the first square, 1 times 1, 1 times 1. Area of the second square is going to be root 2 over 2 times root 2 over 2, which is 1/2. And so right at that point, you know the pattern. This is going to be 1/2, this is going to be 1/4, this is going to be 1/8. If you wanted to, you could go further and say, okay, if this is root 2 over 2, then this is root 2 over 4, and then figure out the length of this and find the area of that. You're going to end up with 1/4 and then 1/8 and that kind of thing. You can also just kind of look at the diagram. Here's this, and if we were to, let's see, try to make this not super messy, but if we split it up like that, do you see that this is half of this whole square? So the inside square is half of the outside big square. And then the same thing would hold true for each of these little sections. Okay, so the area of each of the successive squares is being multiplied by 1/2, as we see here. The value of our first term, meaning the area of the big square, is 1. So the infinite sum would be a sub 1, meaning 1, over 1 minus r, and dividing 1 by 1/2 gives us 2 square centimeters. So the area, this is sort of divided up like this. The sum of the areas of all the squares would be 2. The sum of the big square, or the big square, is 1. Pretty neat. And if we're looking at perimeter, these numbers are a little messier, but not too bad. Find the sum of the perimeters of all the squares. So the outside square has a perimeter of, well, it's 4 sides, and they're each 1, so 4. The second square, we established that the side has a length of root 2 over 2, so 4 times that is 2 root 2. And if you did the same for the third square, we would end up with 2. And so we're seeing that this common ratio is 1 over root 2, so that's what we're multiplying by. 1 over root 2 we remember as this. Okay, so we're multiplying by root 2 over 2 each time. And instead of working through all the details because I don't have space or time, you might want to just verify that to yourself, or you could just trust me. Anyway, for a value of the first term, so the perimeter of the biggest square is 4, common ratio is root 2 over 2. So then we do some math, and we find that the infinite sum is a sub 1, value of the first term, over 1 minus r, common ratio. We do common denominator, turn this into 2 over 2, multiply by the reciprocal, conjugate, FOIL, distribute, and then divide 2 into each of these, giving us this, and the units would be centimeters because we're talking about length or perimeter. Okay, so before you go, hopefully you haven't turned this off yet. Look, this might be really helpful to you. So this is just a summary of what we've been talking about, so you might want to you have some blank space in your notes, you might want to write that, and you could pause it. And what we get is this. So this would be a quick reference, right? You have this available to you whenever you're working through this. So for arithmetic, here's just a description or a summary. What are we talking about? Well, you add something every time, and D is the common difference. Whereas in geometric, we multiply by something, and R is the common ratio. So here were those general formulas for recursive and for explicit formulas, and then for the sum of n terms, and then for the sum of an infinite. Remember, this only works for convergent, and I'm just going to keep it simple and say, no, that we got to be technical here. So the absolute value of R has to be less than 1 in order for the series to converge. And nope, if it's arithmetic, it's never going to converge to some value and get closer and closer to 0. So there you go. Nice summary. Thanks for listening.